Okay, so in the last class we discussed up till here and we saw how the force is transmitted through the sample, and when we have a shear plane, how to assess the forces in the shear plane. So what we do is we take out this triangular wedge, and all the stresses which are acting on it, and then we convert that into forces. So here we have the sigma n, all right, or the sigma theta in the normal direction. So while drawing, some deflection has been there, so you can consider this to be the normal direction. Okay, and we have the two planes. So this is one plane and this is the other plane, perpendicular plane, and this is the angle theta. So what we do is, so suppose if we consider this to be area A, so if this is area A, then obviously this is A sine of theta, this area, and this area is A cos of theta. So the force is sigma theta or sigma n into A. That is the force here acting on this direction, right, in the horizontal direction. That is sigma theta or sigma n into A. So one force we got. Then we have to find out what are the other forces. So here definitely this is sigma 3 into A sine theta. So that is the force sigma 3 into A sine of theta. That is the force. And here sigma 1 into A cos of theta. So this force we have to again resolve it into two components. So one component in this direction, one component in this direction. So this component will be added up to in this one, for because this is the summation of fx, okay, this is the summation of fx. So sigma n or sigma theta into A is equal to, so this is sigma 3 into A sine of theta. Now if this is theta, definitely again, so this force, this component of this force is sigma 3A sine theta, right? So we have sine square theta, that is. So similarly here we have this component. So this is the component here. So if this is theta, so we have sigma 1 A cos theta into cos of theta again. Alright, so this is sigma 1 A cos of theta is this force. So the component of this force in this direction, in the horizontal direction at an angle of theta, is sigma 1 A cos of theta into cos of theta. So cos square theta. Alright, similarly you have to find out, so tau theta into A. Tau theta into A is the force in this direction, and we have to find out the force in the, so here all the forces under downward direction, so plus, alright, so we can say here plus, so that is sigma 3 into A sine theta. Again if we consider this component, so this is cos theta, so sigma 3 A sine theta into cos theta. Again here also it is in the downward direction, so plus sigma 1, so this is sigma 3, sigma 1 into A cos of theta into, so this is sine of theta, this component of this force, so that is into sine of theta. So similarly if you have a shear stress here, tau, so just like this only, so this is tau suppose, so the force will be tau into A sine of theta, that is the force. So that force again, so if this is sorry, if this is tau into a sine of theta, all right, then you have to resolve it into two components again. So one will be in the vertical direction, one will be in the horizontal direction, and this is the angle theta. So this will be tau a sine theta cos theta, and this will be tau a sine square theta. Okay, so you have to resolve it into two direction, one in the y direction and one in the x direction, and the forces in the x direction you have to add up, and the forces in the y direction you have to add up, and ultimately you will, if it is major principal planes, so you will arrive at theta, which is at any angle theta, at any plane inclined at an angle theta. So we have this normal stress, normal stress, and at any plane at inclined at an angle theta, we have the shear stress. Okay, we have the shear stress. So kindly remember these two equations because we are going to use that. And if there is another tau, so as I have shown here, so here you see, here I have shown, so this is tau a sine of theta. So this force, tau a sine of theta, it adds up here. Okay. So similarly, this tau cos theta sine theta will be for the other one. So here, if it is tau, so here in this direction. So if this is tau, so in the other direction, the tau will act. Right? The shear stress will act in the other direction. So one thing you always remember is that if there is an element, so if we have a shear stress in this direction, then we will have a shear stress in this direction on this plane, perpendicular plane. So why is that? That is because of the rotational equilibrium. Alright, so this element, it is not undergoing rotation. So definitely whatever shear force is acting in this direction, same amount of shear force has to act in the other direction. Okay. So these are the equations here. Alright, so we have, if there is a shear stress on the planes, so on a plane inclined at an angle theta s, so we have normal stress and we have shear stress. So if we do not have this, so if this is 0, so this will be the major principal plane and minor principal plane. So in that case, this will become 0. This will become 0. Okay, because this is 0, this is 0. So what we are going to today understand is that regarding the Mohr stress path, all right, and how the Mohr circle develops. So Mohr circle is a representation of the stress state of the soil or stress state of the sample, basically of any element. Representation of stress state. So if I say pore pressure, so pore pressure is same in all direction at a point. That means on any plane you take, pore pressure is always acting normal to that plane, and it is the intensity of the stress or the magnitude of the stress is same. The value of the stress is same. So at all direction, the pore pressure is same. But in case of stress, it is not like that. Stress, what happens is that, so we have a solid object, or a solid element, we can say. So on this solid element, on all planes which are parallel to this plane, we have sigma 1 acting. So if this plane we consider, so sigma 1 is acting on top and sigma 1 is acting on the bottom. So if we consider the top part, so this is the force or the stress acting on the top part here. If we consider the bottom part, alright, so if we consider this element here, so we have sigma 1 here, sigma 1 here. Alright, So sigma 1 is acting at the normal this planes or these horizontal planes at all points of this element. Similarly, if we consider the horizontal planes, if we consider the vertical planes, if we consider the vertical planes, so sigma 3 is acting on the vertical planes. So here, if we consider this element, so this element also, so here we have sigma 1 on top and sigma 1 at the bottom, and we have sigma 3 and sigma 3 at the sides. So on all vertical planes we have sigma 3. Now what about the orientation of the planes? If the planes are changed, so if we have a plane inclined at an angle theta to these two planes, alright, so this is basically theta. Okay, so this is theta. So in that case, what will happen? How to represent that? So to do that, we again take help of what we have done here. Alright, so we take help of this force equilibrium, and we ultimately find out sigma theta and tau theta, and we ultimately see that sigma theta, or the normal stress on the plane inclined, is a function of the inclination of the plane as well, right? Considering sigma 1 and sigma 3 to be acting on the planes here. Okay, so that part you have to understand and visualize. Okay, and now so we will have understand how the, so now again we come back to the triaxial test. Okay, so in the triaxial test we have a sample. So in the sample, what we do, we apply the confining pressure from all around. So basically it is axisymmetric condition. Axisymmetric condition. So sigma 3 is, sigma 2 is equal to sigma 3. So sigma 3 is actually acting radially in all directions. So if we observe one cross section, so one cross section like this, so sigma 3 is acting on all direction radially inward. Right, so one cross section here like this. So on all vertical planes, we have sigma 3 acting. You rotate the plane in any direction, not about the z axis, alright, so you rotate the plane about this axis, about the axis of the sample, about this axis. So you rotate the plane in this manner about this axis. So on all vertical planes, we have sigma 3 acting, and on all horizontal planes, we have sigma 1 acting. So we can approximate the stress condition to this configuration here. Alright, what is happening in the sample? So we have sigma 3 from the sides, alright, using the water pressure, sigma 3, and sigma 1 from top. Okay, and ultimately we go on increasing sigma 1, and at a particular value of sigma 1, the soil sample shears, as we have discussed yesterday. So this is the limiting shear resistance of the soil. So at a particular value of sigma 1, this sample fails. Alright, and when we do the test, we actually observe that the reaction from the, as I have told yesterday, we measure the reaction from the sample using the, so the sample is moved up, alright, and it is placed on a rigid plate and it is moved up, and the reaction from the sample is measured using the proving ring, alright. So as this goes up, the proving ring compresses and we measure what is the reaction. So when the sample shears, the soil cannot put more load onto the proving ring and the load decreases. Alright, so we have this kind of curve, and this is the maximum load that it can take. Alright, of course, we will see when we will define for the various shear strength definition, we will see. Okay, and this is in case of normally consolidated, it is like this. So it goes on deforming at constant value of this sigma deviator. Alright, the sigma deviator. So that part you have to first of all understand. Now, so these are the various elements of the Mohr circle. So the thing is how the Mohr circle grows. Alright, so how the Mohr circle it grows. So if you again recollect what we have discussed about the triaxial test. So in the triaxial test there are two steps. One is the consolidation, alright, or cell pressure application, basically not consolidation. I cannot the cell pressure application. The cell pressure application, if it is undrained, then it is unconsolidated. If it is drained, then it is consolidated. So that is cell pressure application. If you remember what we have discussed, then once we have attained the requisite condition of consolidation or effective stress state, then we go for shearing. So that is the step 2, so shearing. Alright, so shearing can occur again in two cases. One is undrained case and one is drained case. So if it is undrained case, then there is no volume change and there is change in pore water pressure, that is development. So either pore water pressure increases or decreases. And if there is drained shearing, then the volume either increases or decreases depending on whether the soil is over consolidated or normally consolidated. So we have discussed all of this in detail in the previous classes. So I would like you to recollect all those things because again we are going to ultimately converge to a particular concept so that we can define how the soil will behave. So now what we do, so here we have applied the cell pressure. So we have applied the cell pressure, so we have sigma 3 here and we have sigma 3 here. So all around we have sigma 3. Okay, so this is cell pressure. And we are measuring the pore water pressure. So no drainage is allowed here, alright, for now. And we are measuring the pore water pressure and we see that there is some amount of pore water pressure here. So if you remember, we have the total stress, so and we have the pore water pressure. So total stress minus pore water pressure, we get the effective stress. So we have this total stress point. So now here you will see at the starting point when we are applying cell pressure, at all points everywhere around the soil we have only the cell pressure. So sigma 3 is equal to cell pressure sigma c, and sigma 1 also, if we consider this to be the major principal plane, so whatever stress is acting on this plane is sigma 1 is also equal to the confining cell pressure, which is equal to sigma 3. So if you remember the equation again, so at any angle, at any plane inclined at an angle theta, we have sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos of twice theta. So since sigma 1 is equal to sigma 3, this term becomes equal to 0. Sigma 1 equal to sigma 3, so we have twice of sigma 3 by 2 is equal to sigma 3. So on all planes, so it is now sigma 3. Alright, so we have sigma 3 here. Okay. And what about theta, tau theta? So this is tau and this is sigma. Alright, so what about tau theta? So we have sigma 1 minus sigma 3 by 2 sine of twice theta. So what is sigma 1 minus sigma 3? It is 0. Ultimately tau theta is equal to 0. So it is at 0, this point. Alright. So what is effective? So sigma dash is equal to total stress, which is sigma 3, or sigma C, cell pressure, applied cell pressure, minus the pore water pressure, whatever we are measuring. So that is the effective stress. So this difference is the pore water pressure. And this is the effective stress, sigma dash. Again, tau theta is dash is also equal to 0. And this is total stress, sigma. Now, so for some, this first, to understand the things properly, so what we are going to do, we are going to neglect first of all this effective stress. So let us for a while leave aside what is happening in the effective stress. Let us concentrate on the total stress only, right? So we have applied sigma 3. So we have applied sigma 3. And now here also we have sigma 3 and sigma 3. Alright. And we have applied sigma d. We are applying sigma d. So now we have here on this plane, if I draw it in a bigger way, so we have the sigma 3 from the water in the soil, water in the cell pressure, the cell pressure whatever we have, this is the sigma 3, alright. And apart from that we have the deviatoric stress as well. So this is now sigma 1, which is equal to sigma d, the stress from the loading ram distributed across this plane by a rigid plate over here. So through the rod we have a rigid plate and on the sample. So this stress is distributed all to the sample equally. And we have the sigma 3 as well on top of the plate. Alright, so sigma 1 is equal to sigma d plus sigma 3. Okay. So what is sigma d is equal to sigma 1 minus sigma 3. Now this is very important because this implies the diameter of this Mohr circle. So sigma 1 minus sigma 3, we have this difference. Just like here we have the pore pressure, so total stress minus pore water pressure, we arrive at the effective stress. Total stress minus pore water pressure, we arrive at effective stress. Here sigma 1 minus sigma 3, we have sigma d. Alright, so sigma 1 minus sigma d, we have sigma 3, we have sigma d. Okay, so now we apply sigma d, suppose 1 kilonewton. So the diameter of this will be 1 kilonewton. Then we apply 2 kilonewton. So 1 kilonewton, then 2 kilonewton we are applying. So the diameter increases to 2 kilonewton. Are you getting this? I will show you one Excel I have made. I will show you again while plotting the things. So 1 kilonewton, 2 kilonewton, 3 kilonewton, as we go on increasing the deviatoric stress. So this is strain versus deviatoric stress, like Q, which is equal to sigma 1 minus sigma 3 is equal to sigma D. So this is Q. Alright, so this is Q is equal to sigma D. This one, which we are applying from the loading RAM. Okay, so as we are going on increasing this load, cell pressure is remaining constant. So cell pressure we have applied whatever. So suppose we have applied 200 kilonewton cell pressure. So cell pressure is remaining constant. So sigma 3 is remaining constant. Sigma 3 is remaining constant. And as we are applying this deviatoric load, we are going on increasing this deviatoric load. The diameter of the Mohr circle is going on increasing. Now what does that mean? Alright, it is going on increasing. Now what does that mean? What is the significance of this? The significance is we have this element, the soil element. So we have sigma 3 in this direction, sigma 3 in this direction. And we have sigma 1 here and sigma 1 here. So when sigma 1 was equal to sigma 3, on any plane which we draw here, on any plane, inclined plane, inclined at an angle theta, on any plane you consider, the shear stresses was 0. That means this element, this soil element or this soil sample was subjected to only compressive stresses, mean compressive confining stress. It was subjected to only compressive and confining stresses. But as soon as sigma 1 is being applied, so now what we have, so we will have now development of shear stresses. Now the shear stresses at various planes will develop according to the Mohr circle. So here you see, so this is the plane. This is of course obviously the failure plane. So what is, suppose we consider angle A. So what is the stress condition at an angle A? So it is twice A. So if this angle is, this is A, so this is the stress condition. So this is the shear stress and this is the normal stress on that plane. Alright, if we consider an angle, suppose B, alright, so this is angle B, this is angle B, this is twice B, sorry, this is twice B, and this is twice, suppose C, this is C, alright, so A is already being shown, so this is C, so and this is twice B. So what is the stress condition at an angle, on a plane inclined at an angle B? So this is the stress condition, this is the shear stress and this is the normal stress. So the Mohr circle basically defines the stress state, or at a point. Alright, so it defines all the planes, it includes all the planes passing through that point. Alright, so that is the concept of the Mohr circle. Now when we will go on loading, alright, so here you see, so this is the equation. Alright, so we will see again, I am showing one plot. So we are going on loading, and ultimately after certain value of load, so here we have the proving ring, and this soil sample, it is going on, it is moving up and up and up, but after a certain value of force from the proving ring, that means the soil, it cannot exert any more force. It will not exert force. Alright, so just as the friction which we observed yesterday. So if we have a normal stress here, alright, and we apply a force, so when we go on increasing the force, ultimately at a point, this mass will start to move, and the force required to keep it in motion will decrease. And this is the force which will require it to just keep on moving the mass. So similarly here also, this soil will fail, it will shear off. So to keep this sample shearing at a constant rate, all right, so that rate is obviously the rate of this motion of this sample up towards upward direction. All right, so at that rate, this much of force is, or this much of stress is required. That this is the Q, this is the ultimate or the maximum Q which the soil can take, deviatoric stress which the soil can take. So we go on shearing the sample, but Q does not increase. The sample is going on shearing, so strain is increasing. All right, the strain is increasing in the soil. The strain is increasing, but the soil, it cannot take any more load. So strain is increasing. The mass is moving, but it cannot take any more load. All right, like this. So this is the load to keep it on a motion. So similarly, this is the stress to keep it on shearing rate. I mean, at constant shearing. So this is the strain, and this is the shear. All right. Now, so this is the total stress. Now to define the shear strength of soil, we cannot consider this total, we should not consider this total, stress Mohr circle. We should not consider this total stress Mohr circle. All right. So this is the total stress Mohr circle at failure. At failure of the soil. So it cannot take any more load. So this is the condition in the soil element when we are applying the increasing the load. All right, it is going on increasing. It is going on increasing. All right, it is, so the load and the strain is increasing. Yes, anyone want to say something? Anyone want to say something? Okay, so this is the strain and this is the deviatoric load. So sigma D or Q, whatever you say. So this is the increment. So Q is increasing. So 1 kilonewton, 2 kilonewton, 3 kilonewton, 4 kilonewton, 5 kilonewton, like this it is going on increasing. So with increasing load, strain percentage is increasing. Alright, so the soil is getting compressed. So 0.1%, 0.2%, 0.3%, 0.4% it is, so of the actual length it is getting compressed. So that is the strain. So stress versus strain, alright, or deviatoric stress versus axial strain. So that is what we are plotting. So as it is going on increasing, so from here we started, so as here we are starting, so as it is going on increasing, this Mohr circle is also going on increasing. That means the stresses at the various planes of the sample, alright, it is increasing in this manner. It is increasing in this manner, and it is increasing, and it is not going beyond this. So to understand what has happened, we need to, so here as we have discussed, so we are actually measuring the reaction from the soil. So the soil has already field, it is constantly shearing, and it cannot give any more load. It cannot compress the proving ring any further. Therefore, the proving ring, that much of load, whatever it is giving right now at this point, it is sufficient enough to keep the sample shearing at the rate it is going up. Alright, whatever rate it is going up. So it may be going up at 1.25 mm per minute. Alright, or 0.625 mm per minute. Alright, so whatever rate it is going up, obviously the way, the effect of the strain rate we are not considering here. If time permits, we will see that afterwards. So the effect of the strain rate we are not considering. We are considering that it is going up at a rate. So to maintain the shearing at constant rate, at that rate, this much of load is the maximum that is required. Alright, so it is given by this proving ring onto the sample, or actually that is what the sample is giving onto the proving ring, and we are measuring that. Okay, so that is the action and reaction what is happening between the sample and the proving ring. So this is the cell pressure, that is the cell pressure. So this is the cell pressure. Alright, and this total cell pressure, so cell pressure plus sigma D is the sigma 1 at failure. So cell pressure plus sigma D is the sigma 1 at failure. So we have now a failure state. So we have sigma 1 and we have sigma 3 at failure. Okay, so now we concentrate on the effective stress state. Alright, the effective stress state. So we know that we have initially seen that this is the pore water pressure. So this is the pore water pressure. And what we are going to do is we are going to shear the sample in a drained state. Alright, so drained shearing we are going to do for now. So drained shearing. And we are going to maintain this pore water pressure as a hydrostatic pore water pressure. So what does that mean? So that means in triaxial terms we call it back pressure. We call it back pressure. So while shearing, this pore water pressure will be maintained. So that is the U. Alright, and since it is a drained shearing, so there will be no delta U. So delta U will be equal to 0. Alright, in fact we will see what is the case when there is an undrained shearing. Okay, we will see that as well. So now, since there is no delta U, so this difference in effective stresses, this pore water pressure will be remaining maintained. It will remain constant. Okay, so what will happen is that as we go on applying the deviatoric stress, now the effective stress will also increase. So if you remember, so sigma dash is equal to sigma minus U. Okay, but in case of deviatoric stress or Q, alright, it is ultimately equal to sigma deviator or effective. The effective stress, the pore water pressure has no effect on the deviatoric stress. So how can we know that? So sigma D we know is equal to sigma 1 minus sigma 3. all right. So if we write it in terms of effective stress, so we have sigma 1 minus u, all right. So sigma 1 dash, that is minus sigma 3 minus u, sigma 3 dash. So ultimately if we take it out, so this becomes plus, so we have sigma 1 minus sigma 3 minus u, minus plus minus minus plus u, so these two gets cancelled, so we have sigma 1 minus sigma 3. Okay, so sigma d is equal to sigma d dash. So it has, pore water pressure has no effect on the deviatoric stress. Alright, so that is one of the critical point that we have to note, because when there is shearing, if there is undrained shearing and there is development of pore water pressure, so it reduces the effective confinement, but the deviatoric stress, it is remains unaltered or unaffected. So it shears at a very low value of deviatoric stress. So we will see why that is. When you understand how the Mohr circle evolves and how the stress state evolves, we will understand that. So as we go on increasing here, so the pore water pressure or the back pressure will remain constant. So we have the U constant at this difference. So this difference will remain constant. So whatever we have, so sigma 1 dash will be equal to sigma 1 minus U, and sigma 3 dash will be equal to sigma 3 minus U. Okay, so that is the effect of the hydrostatic pore water pressure. It only just shifts the Mohr circle. Alright, so here what happens as we go on now applying the deviatoric stress, so delta U is equal to 0, U is constant, so this difference is equal to this difference. Okay, so what is this one? What is this one? So this is sigma 3 minus U is equal to sigma 3 dash. So sigma 3 dash. And what is this one? So this is sigma 1. This is sigma 1 minus U is equal to sigma 1 dash. So equal to sigma 1 dash. So U is remaining constant, that is hydrostatic pressure, or in triaxial terms we call it the back pressure. At constant back pressure is maintained, and we do the shearing in a drained condition. Alright, in a drained condition means excess pore water pressure is equal to 0, delta U. Okay, so as we go on increasing the deviatoric stress, axial strain will occur, so the soil will get compressed. So that means actually soil is moved up, and when it is moved up, it is applying force onto the proving ring. The same amount of the proving ring is also getting a little bit compressed, and it is applying the same amount of load onto the soil. And from the compression in the proving ring, alright, so K into X, so K is the proving ring constant, X is the displacement or compression in the proving ring. Alright, so from there we measure the sigma D, and obviously axial strain we can measure. So whatever is the compression in this sample we can measure, that is the axial strain, and with increasing axial strain the sigma D is also increasing, and sigma 1 dash and sigma 1 is also increasing at the same difference of pore water pressure U. Alright, so it is increasing, and ultimately it will stabilize at this deviatoric stress. So it will stabilize at this deviatoric stress. So why it stabilized at the deviatoric stress? Because now it has reached its failure state. Okay, so this is tau is equal to sigma n tan of phi. So this is the failure Mohr-Coulomb failure envelope, and the Mohr circle and stress state in the soil, the stress state in the soil, so sigma 1 and sigma 3, so sigma 1 dash, actually sigma 1 dash and sigma 3 dash, it has reached the failure state, and this is twice the inclination of the failure, so twice of theta. Alright, so that is, so this is 45 degree minus 5 by 2. Alright, so that is the failure plane. Okay, so that it has failed. So in this manner we go on increasing the deviatoric stress. So as we go on increasing the deviatoric stress, the diameter of the Mohr circle is getting on increasing. That means on the inclined planes, on the planes inclined to the minor principal plane and major principal plane, shear stresses are getting developed. So this is the shear stress. Alright, so this is shear stress tau. Alright, and this is normal stress sigma. Okay, so shear stresses are getting developed. So the shear stresses are getting increased, and ultimately at a point it will reach the failure state, and the soil will constantly deform and constantly shear at that particular value. Alright, and it cannot take any more deviatoric load. It cannot take any more deviatoric load, and constant shearing at constant volume, if it has reached the critical void ratio state, it will occur. So what we do, we obviously do 3-4 tests. So we apply, suppose here 100 kPa cell pressure. Alright, here we have applied 200 kPa cell pressure, and we have applied 300 kPa cell pressure, and we have maintained the back pressure U at suppose 50 kPa. So what is the sigma 3 dash here? It is 50 kPa. So this is sigma 3 dash in this case. So if U is maintained 50 kPa in all of the cases, so we have here sigma 3 dash is equal to 150 kPa. So this is sigma 3 is equal to 200 kPa. Alright, the pressure in the water, and the pore pressure is 50 kPa. Pore pressure is 50 kPa. So the effective confinement is pore pressure minus the cell pressure. So that is this one. So here it will be sigma 3 dash is equal to 250 kPa. So likewise we again apply the deviatoric stress. We apply the deviatoric stress through here. This is a rigid plate. So this is a rigid plate. Alright. So sigma 3 we have, and this is sigma D, and this is sigma D. Okay, and ultimately we will see, so this is for this one, this Mohr circle is for this one, and this Mohr circle is for this one. Okay, so we will have 3 failure deviatoric stress, so deviatoric stress at failure, right? And ultimately we will draw the tangent. So this part actually comes after we draw the maximum Mohr circle, the biggest Mohr circle of the test. Alright, of the test. After drawing that, we draw the tangent, and we get the Mohr-Coulomb failure, line, or the failure plane, right? So in that case, so here you see, so this is sigma 1 minus sigma 3 is this one. Sigma 1 minus sigma 3 at failure is this one. right? So this is sigma 1 and this is sigma 3, and this is sigma 1 for this circle and this is sigma 3, right? And this is 248 kPa, so that is this. Okay, so this is a drain case. Now we will consider the undrained case. Alright, so again we will start from the same initial condition. So we have this effective, this is the total stress, so we have 200 kPa. Cell pressure, we have 200 kPa cell pressure, and the pore water pressure is suppose 100 kPa. Alright, the pore water pressure is 100 kPa. So we have the effective stress sigma 3 dash is equal to sigma 3 minus u. So sigma 3 is 200 kPa minus u is 100 kPa, so that is the back pressure. Alright, so that is the back pressure, so it is 100 kPa. So it is sigma 3 dash is 100 kPa. So this is sigma 3 equal to 200 kPa. This is pore water pressure is equal to 100 kPa. So sigma 3 minus pore water pressure, we arrive at the effective stress, which is equal to sigma 3 dash is equal to 100 kPa. Now above what we did was drained, so there was no generation of excess pore water pressure. Alright, so the way the total stress Mohr circle developed, the same way the effective stress Mohr circle also developed, because I have shown that the pore water pressure is remaining constant, so that delta U is 0. So we have the hydrostatic pore water pressure U, which is this minus this. So sigma, this is sigma 3 and this is sigma 1. Now in case of undrained condition, so now we are applying undrained condition. Okay, so shearing is undrained. Okay, so when shearing is undrained, so there will be delta U, pore pressure generation. So the as we go on increasing the this sigma d, as we go on increasing the sigma d, so the pore water pressure will also increase. Okay. Now considering the pore water pressure increment only due to effective, only due to the mean, increase in the mean confinement. All right, only due to the increase in the total mean confinement. So if I consider that, so initially the confinement was sigma 3, total confinement was sigma 3, so at all directions we had sigma 3. Okay, but then we applied sigma d. So now sigma 1 is equal to sigma 3 plus sigma d. Okay, and again, so sigma mean, if you see, so what is the mean? So sigma mean is, the sigma mean is sigma 1 plus sigma 3 by 2. Alright, or we can say S. Alright, so ST plot, in the ST plot, S is equal to sigma 1 plus sigma 3 by 2. Now, initially when sigma 1 was equal to, or sigma 1, I mean sigma d was equal to 0, so sigma 1 was equal to sigma 3. So in that case, we had S is equal to sigma 3. So now what we have is S is equal to, so sigma 3 plus sigma 3 plus sigma d plus sigma 3, that is this one. Alright, so we have replaced sigma 1 with sigma 3 plus sigma d by 2. Okay, so if I then, so if I, this is suppose initial and this is final. Alright, so here if I take this out, so we have sigma 3 plus sigma d by 2. We have sigma d by 2. So what is delta S or delta sigma m? So that is equal to sigma initial minus sigma final, which is, so sigma 3 is getting cancelled, so sigma 3 gets cancelled, so sigma 3 gets cancelled, and we have delta S is equal to sigma d by 2, or sigma mean is equal to sigma d by 2. Alright, so that means the effective confinement, the total confinement of the soil will increase by half of deviatoric stress, whatever we are applying, because sigma d is actually ultimately it is like the center of the Mohr circle. So this is what the mean confinement it is showing, total mean confinement. Alright, so this is sigma d. If this is sigma d, as we have seen earlier, just now we have discussed what is sigma d. So sigma d by 2, this is sigma d by 2. So this is diameter and this is radius. So in normally consolidated case, we will have delta U is equal to delta sigma mean or delta sigma S. Alright, the effective confinement will increase. So that will be equal to sigma d by 2. So this case also we have discussed when we did the constant mean and extreme principal stress for doing the liquefaction test, liquefaction triaxial test. So we discussed the constant mean and extreme principal stresses. So delta U basically increases by sigma d by 2. So what will happen here is, so as soon as we increase sigma d, here, so the effective stress circle will shift by sigma d by 2, because initially it was U, So as soon as I give this much of deviatoric stress, this much of sigma d, so the pore pressure will increase by delta U is equal to sigma d by 2. So now the pore pressure will be, initially it was U, so this is U plus sigma d by 2, this much. Okay, so what will happen is that the mean will remain at that point. Alright, and the effective stress in case of undrained condition, it will grow about that mean like this. And obviously, as we know that there is the A parameter. Alright, so we have delta U by delta sigma 1. Alright, so we have the A parameter. So for that, so during shearing also, the pore water pressure will again increase. So that extra amount of increase will cause the mean to shift in the left direction. Okay, and ultimately it will fail at this position. So it will take shear and it will fail. In some cases, now in most of the cases it may go in the constant deviatoric stress. All right, if it is at a already at a critical state. All right, if it is In a dilative state, there will be negative pore water pressure. Again, it will trace back, and the Mohr circle will increase in diameter. And if it is in a normally consolidated state, there will be dropping of the shear stress. So how it drops? So when the pore pressure develops, the mean will shift to the left. The mean will shift to the left. Okay, and you see that this is the maximum amount of, actually this is the maximum amount of shear that the soil can take. Alright, so for this condition, so this is the failure point. So as we go on increasing the deviatoric stress, or as we go on, loading the sample, so what will happen is that the pore pressure will develop and the mean will shift to the left. So in that case, it cannot take any more load, alright, because effective confinement in the soil is decreasing, and therefore we will have a failure of this kind. Alright, so it may also, this is what is the flow failure that we have discussed in the liquefaction. Like the flow failure that we have discussed in the liquefaction chapter. All right. So pore pressure is what is developing here. All right. Now I need you to understand the concept of this sigma d by 2, increment of delta u is equal to sigma d by 2. Okay. So that is what I have shown here. So initially the confinement, the effective confinement was sigma 3 plus sigma 3 by 2 is equal to sigma 3. So that is sigma mean. So this is the initial condition here in this case. Okay, then as we applied deviatoric load, so the mean got shifted here. Okay, so now we have sigma 1. This is sigma 1, sorry. So sigma 1 is equal to sigma 3 plus sigma d. So if we place it there, so this is sigma initial, and in case of sigma mean final, we have sigma 3 plus sigma d plus sigma 3, which is this one, alright, by 2. Okay, so this will give us sigma 3 plus sigma d by 2. So the increment is from sigma 3, which was initially the cell pressure, which was the initial cell pressure. So from sigma 3, now the confinement, mean confinement has increased by sigma d by 2. Now when this undrained case, as we have discussed earlier in our previous classes, so in undrained case, whatever load we apply, the effective, the mean confinement, so that much of increment in the pore water pressure takes place. All right. So the soil effective stress remains unchanged. So that is what exactly happening here. So if I have a circle, so if this circle is here, so this is sigma d. If I shift it by sigma d by 2, so the mean will shift from here to here. So the mean will remain constant there. Alright, obviously after certain amount of shearing, alright, due to the shearing, there will be development of excess pore water pressure. More amount of excess pore water pressure, not only due to the confinement, due to the shearing itself. Alright, and the soil will try to compress, so it is not getting compressed. So in a normally consolidated soil, when we shear the soil, it tries to get compressed, but it is not getting compressed because we are preventing the drainage. So therefore there will be excess pore water pressure generation, and now in this case the mean will also shift, and when it shifts, so ultimately it will touch the failure surface here. Okay, and after that, if it is in a very loose state, alright, if it is in a very loose state, so excess amount of pore water pressure will be generated and there will be a decrease in the deviatoric stress, right? So decrease in the deviatoric stress. like this. Now the soil will constantly shear at this value. Alright, and as the sample is moved up, the proving ring will constantly show the value of this state. Okay. Now here what I have is, so this is a UCS test result. UCS test result. Okay, so here you see delta H. Delta H means if this is the sample, so there is a compression delta H, delta H, delta H, alright. So it is changing, the H is changing. So this is the delta H. Axial means compression, axial compression of the sample. This is the force which is applied through the ram. Alright, and it is reading, the reading is done in the proving ring. Alright, so this is the force. So force divided by the area of cross section of the soil sample will give you the deviatoric stress, sigma d. Okay, sigma d. And this is the strain.